Okay, good morning, everyone. So today we're going to continue our study of Prim's algorithm, and in particular, we're going to look at designing a small package to solve Prim's algorithm on weighted graphs for using Python. Okay, so in order to do this, we need a test graph. Here is a test graph that I have from yesterday. So let me just redraw it for you. So you're gonna have it kind of big up here. So yeah, node 0. So vertex 0 goes to vertex 1. Uh, Vertices are also called nodes, and a vertex can also be called a node in these applied settings like this. So if I say node, I mean vertex. If I say nodes, I mean vertices. Okay, so that, and then node 3, this, and then node 4, that, and then node 5 over here, and there are the connections, and then there are weights associated with each of the edges. So we have 2, 3, 1, 1, 1, 4, weight 2, and weight 5. Okay. So you might ask yourself how we can store this graph information in the computer. Well, we do that in several different ways, but what we're going to do is we're going to use a weighted edge list, and we're going to save this on our computers as a .txt file or a text file. So I'm going to call this graph g1.txt. So that's what I'm going to save it as in the computer. And the weighted edge list is going to be as follows: 0, 1, and there's white space here, by the way. 0, 2, 3, 1, 2, 1, 1, 3, 1, 2, 3, 1, 2 to 4 with weight 4, 3 to 5 with weight 5, and 4 to 5 is weight 2. Okay, so what this is a list of all the edges in the graph together with their weights. So for example, node 0 goes to node 1 with weight 2. 0 to 1 with weight 2. Node 2 goes to node 4 with weight 4. And this is an undirected graph, so 4 goes to 2 with weight 4 as well. Okay? So because graphs are nothing more than relational objects defined by sets on vertices and edges, this is just a picture, but really this is a collection of sets, like a vertex set and an edge set with weights. All the information encoded here is in this list. Anything that you can find out about the graph in the picture, you can find out from this list if you just translate it, okay? So when dealing with computational graph theory, you often store your graphs in some list, and that's all you really need to work with, okay? So our goal is to solve the minimum spanning tree problem on this graph, or on a general graph, right? So the goal of the project, right, okay, is to solve the MST problem using Prim's algorithm. Okay, and the previous few lectures that I've posted have gone into the details behind how we do this, right? And we've talked about Prim's algorithm, and in my most recent YouTube video, I broke down each of the steps required to solve Prim's algorithm, right? So maybe I'll write it up here for reference, just so we can remember it, right? So the way that Prim's algorithm works is we're going to initialize. Well, actually, no. You can look at your notes to find Prim's algorithm. I think it's more important now that we start talking about implementing this in using Python in kind of a, with the goal of designing a package to do this for someone else. That's the whole goal here. One of the reasons why I like to do this with my discrete math students is that at the end of the class, if you do this correctly, you have a nice little package that you can provide to maybe future employers, say, hey, this is one thing I've done, look at this, right? So you can put it in like a portfolio that by the time you end up graduating, you should have like a portfolio of small projects that you completed throughout your degree, right? So, okay, how are we gonna do this? Well, what did I name my project folder? So I named my project folder, it's got a long name, Math 2305. Final project fall 2020. So that is a directory on my computer. It's a folder. And inside of that folder, I have another folder called test graphs. And by the way, you should never put white spaces when you're naming your folders and your files. You should always put either dashes or underscores to indicate white space. Never actually put white space. And then I have so this is a folder, and now the rest of these are going to be scripts. So one is going to be called test.py. Another is going to be called main.py. So these are Python scripts. Another is going to be called functions.py. And then finally, we're going to have one called algorithms.py. So the idea is that we're going to take this goal of solving the MSTs and Prim's algorithm, which we could technically do from scratch in one single script. But in practice, when you're working on very large programs, you never put everything into one script. You typically will partition your problem into separate pieces so that if something goes wrong and you get an error somewhere, it's not like you're scrolling through a giant list of things to find the error. You have individual pieces that you can look at, and you can verify that everything in here works, everything in here works, everything in here works, and it makes it much easier to manage these larger projects. Even though this isn't necessarily a large project, it's still, I wanted to emphasize this, I want to emphasize the idea of partitioning your problems into several smaller little pieces. Okay, so let me go ahead and share my screen. Okay. So I've gone ahead and I already have a Spider opened up. Okay. So here is Spider. This is the IDE that I'm going to be using. And what I did is you can see here is I made a new directory right here. So Math 2305 final project, fall 2020. So the way that you do that is you go projects, new project, you find the location on your computer where you want to save it, and you type that name, create, and then you'll have a new, you'll have this little folder over here pop up. Okay. See it right here? So this is the current working directory that I'm in. And then inside of here, I ignore this file here. I have an algorithm script with nothing in it, so it's a Python script. A function script which has nothing in it so far. A main, which has nothing in it. And then I have a test script here, which test is going to be used to build the pieces that go into the individual scripts. And then here, test graphs is a folder. So if you want to make a new folder, just do new folder. And then I've made this folder called test graphs. And test graphs is where I'm going to store all of the graphs I'm going to test my algorithms on. So if I look inside of test graphs, I see g1.txt. Now here is the edge list that I have written on the board. So we have 0 to 1 with weight 2, 0 to 2 with weight 3, 1 to 2 with weight 1, so forth and so on. So this is the graph that I saved on the board, okay? And that graph is stored as a .txt file. So the way that you can do this is new file, make sure that it goes to your correct directory that you're in. So we want to put this file over here in test graphs, and I'll call this like g2.txt. Okay, and then we see that G2 pops up over here in test graphs. Now I don't have a second graph to test on, but I could make one and you can make your own test graphs too. Just draw a bunch of vertices and edges with weights on them, and then put them in and save it, okay? So we're going to be using a Python package called networkx, which will be installed once you install Anaconda. So when you install Anaconda, Anaconda will also install almost every package that you'll ever need, including, so if I go to test, this is where I'm going to test everything out, networkx, okay? So here, we have networkx as nx. So we're importing networkx as nx. Okay. Now, how do we get our graph data? Well, the way that we do this is we first open the file. So notice the first entry here, that is the location of the file you want to open. So I want to go inside of test graphs. Now, depending if you're on a Unix-based system like Mac OS or Linux versus Windows, you will either have / or // okay? So it just depends on your machine. So I'm running Mac OS, so this is the slash that I use to get into test graphs, and then I want to read this file. And this R here is just specifying that I'm reading that file, okay? Now, once I read that file, I'm going to create a graph. Okay, so G is going to be equal to, so I'm going to do nx, so that's networkx, right? Dot read weighted edge list, and then you provide it the graph data that you just read in, okay? And we're going to specify that our node type is int. Now you don't have to do this, but I'm going to go ahead and specify that because all the graphs we'll be looking at will have node type int. Okay, so now if I just click play over here. So I've run that script. So if I look at my variable explorer over here, I see that I have my graph data that I read in, but then also I have G, which is a object, a networkx graph class. So if I type G in my console, I see that. So the way that we can explore the properties of G, we can do something like G dot edges. All right, let's do G dot nodes first. Okay, so notice that this isn't a list. It does give us all the vertices in our graph, all the nodes. But if we look at the type of that thing, it's a class, right? So for our purposes, it might be easier to say that that we convert it to a list instead. So maybe what we can do is say like, so if we do list of G dot nodes, this will be easier to work with. At least I believe so. So if you look at the lectures that I've been giving, I often use V of G to denote the set of vertices, right? So so what if we say like, okay, let's write like a little helper function, and we'll say like def V of a given graph. So we're defining a function now, and let's just return say the list of graph dot nodes. Okay, so this is like just a simple function to convert this node view into a list, and it's using the same notation that we're used to from lecture. So if I run this script again, okay, so now I should have access to that. So I can do V of G. Oh, so it creates it, it makes it into a list. Okay, that seems to work fine. Or we could put it into a set. It really won't matter for our purposes, but this little thing here is going to be a helper function. Instead of having to convert this all the time to a list, we can just call this V, and we have access to it. So now that I know that this thing works, I just tested it. I'm going to go ahead and take this guy, and I'm going to cut it out. I'm going to go to functions, and then inside of functions, I'm going to type that. I'm going to paste it. And then if you see the little star right there, it means I need to save it. So I save it by pressing Command S or Control S. So now that it's saved in functions inside of test, I can just say, okay, from functions. So I'm currently in test, so I can access anything along in here. So I can access each of these scripts. So from functions, import V, which is that function that we just wrote. Right, this is V. Okay, so if I run this, so I should have access to V in my console. So V is V, and then it converts that node view thing into the list. Now, if I do G dot edges, so these are all the edges in the graph. So again, this is not, the type of this is some specific network X class. So in class, I've been using capital E of the graph to represent the edges. So if I go over to functions, I can just do the same thing, say def E of graph. And then we're just going to return the list associated with the edges. Okay, so graph dot edges, like that. So now I have two helper functions, and I hope that you see the pattern here. I'm just inside of functions, I'm putting all the helper functions that I'm going to need throughout writing Prim's algorithm. So go back to the test. Now, if I have more than one function that I want to import, I could say like this, from functions import v and e, or I could just do, I was kind of lazy about it, I could say from functions import star. And that'll import everything from functions. So now I have access to those functions. So I can say, maybe I'll put a print statement in here, print, maybe an f string, the format string. So the vertex set of g is v of g, which is equal to, and then I can pass inside the curly braces, since this is an f string, the function v applied to the graph g, and then close out the curly braces. And then if I copy that, and then I can say the edge set of g, and this is still a string, and then inside the curly braces, I'm going to pass that function e that we wrote inside of here. And again, we've imported those functions v and e up there. So we're getting these errors because it doesn't know what v or e is. And that's because star isn't directly telling it up here. So we can just go ahead and say v comma e just to tell it that that's exactly what we're doing. So then if I run this, there. So these are the vertices in the graph, and these are the edges in the graph. Okay. Now, if you watched my previous video, my previous YouTube video called Iterating Prims or something like this in my YouTube channel, you'll see that there are several steps that we're going to need to do in order to solve Prim, or to implement Prim's algorithm. So one thing that we're going to need to know how to do is to maybe initialize an empty tree. So how do you make a tree using network X? So how do you make a new graph using network X? Well, the way that you do that is you do in X, no, sorry, we'll say that T is equal to in X dot graph. So this makes an empty graph. And we want, so when we initialize prims, we want to start at a vertex or a node. And we're going to have a node set and an empty set of edges. So if I'm looking up here at this graph here, we can start at any node we want. And then that's how we're going to initialize it. So let's go ahead and like write this out. So here's Prim's algorithm. So the first step is to initialize an empty tree. So we're going to say v of t is equal to some vertex v, and the edge set of t is empty. So that's the initialization phase. And then we have the while loop. So while t is not spanning, we're going to, well, maybe I should write it like this. Here's like this bad pseudocode. So v of t equals to v, some random vertex, and e of t is empty. Okay. And then we have the actual algorithm, which is the while loop. So while t is not spanning, can add a min cost edge to T so that T remains a tree. And that's it. Okay, so the first thing we have to do is to initialize our tree. So the way that we can do this, let's share my screen. So we can start with an empty graph like that, and then we can just add a node. T dot add node here. So now if I look at T dot nodes, well, I could probably do this. That's our vertex set. And our edge set is empty. So you can see how these helper functions are really nice. So we could write a simple function to initialize our tree, which is basically this right here. So functions, so maybe def friends initialize. So we're going to need a graph because we're going to pick a vertex from that graph, maybe. And then some node V. And then we just have to say T is equal to nx dot graph. And then T dot add node V. And then return T. So what we're going to need to do here, we're getting an error because we don't have access to network X. We need to import that up here. So import network X as init. Okay, so here I'm going to save that. So I'm going to go back over to test. So now I'm going to import everything. And there's a more professional way to do this that I'll show you in a bit. But okay. So so let's say T equals, but actually we want to make sure that the vertex that we pick is inside the graph. So I guess we could put like a little check. Yeah, we could say something like a quick if statement here. And there's a try except warning that we can do, but I just want to do a quick if we can. So if V not in V of the graph, we want to raise some type of error. Right, so error vertex not found or something like that. And we'll clean this up later. I'm just showing you like the general gist of how we're starting it out. Else. Okay, so save that. Go back over to test. So T is equal to trims initialize. We're going to pass it G. And let's go ahead and initialize at vertex 4. Okay. So the vertex set of T, so we're just going to check it in the edge set of T. We're just having a nice print statement. Okay. Let me put in like a little white space here. Okay. So now if I run that, all right, so there. Now, if we look back at the board, so where did we start? We started right there. So currently, that's my tree, right? So now we need to break down what these pieces mean. So while T is not spanning, what does this mean? Well, as I mentioned in my previous lectures, this means that the vertex set of the tree is not equal to the vertex set of the graph. That's what it means to not be spanning, right? So, okay, that's something that we're going to need to check over and over again. Let's go ahead and write a little simple function to do that. Okay, so we can say, we're going to put this in our function script, so def. So we'll say like is spanning. And we're going to take in a graph and then some subgraph. The subgraph in this case is going to be a tree. But now that we have a simple v function up here, this is pretty easy to write. We just say return v of graph equals, double equals, like Boolean comparison, the the ordering might be different. So because of that, instead of doing a list, I'm just going to say that I'm going to say this is maybe a set for now, and I might change it back. But a set, the ordering doesn't matter. So then when you do the double equals, even if they're ordered differently, it won't matter. Okay. So to illustrate what I'm saying, like if you look at, like, does that equal false? Because the ordering doesn't matter. However, if I do set of 1, 2, 3, does that equal set of 2, 1, 3? And that's true. So that's the only reason why, and I might change it back, but we'll see. I'm going to save this. Okay. Everything looks good. If I go back over to test, maybe, and this print stuff is just so I can check what's happening. This is not going to go anywhere near the final package that will be made. I'm just doing this for myself to see each of the steps in front of me. So I'll use an F string. Is T spanning? And then I'm going to put in curly braces. That is spanning. And again, when we import star, we're importing everything from functions, including this is spanning function. T, comma T. Close off the curly braces. So T is not spanning. So that means that we've entered into this while loop. Okay. So we need to now understand the steps inside this while loop. So we want to add a min cost edge so that T remains a tree. Now this is the important part. T must remain a tree. So what is a tree? Okay, a tree is a connected graph, right, with no cycles. Okay, so yesterday I gave a brief explanation of what it means to be a valid edge, right? What are the possible valid edges? Well, suppose that you have a tree that you're building. Like this is our current tree, just that little dot. Now, could we add, this is a cost one edge. Could we add that edge to that tree and still be a tree? The answer is no, because if we add that edge, then our graph looks like this. And that's not a connected graph. So we cannot add that edge. Okay? The only edges that we can add are ones that keep the graph connected. Right? So we can either add this one or that one. Okay? In general, though, there's a more general rule. If we're building a tree, so suppose we're building some tree, right? That's our tree. We're building it. And if there's an edge that we want to add that has both endpoints outside of the tree, then if we add that to that, we get a disconnected graph. So we don't need to consider edges that don't have endpoints in the tree. If we look at edges that have both endpoints in the tree, and we try to add that, what do we get? A cycle. So if both endpoints are in the tree, then we can't add it, right? We can only add edges where one endpoint's in the tree and then one endpoint's out of the tree. If we're going to remain that we're connected and we don't have cycles. So for example, here, the only edges that have one and only one endpoint in our current tree are 2, 4, and 4, 5. Okay. So let's see if we can find those edges. Okay, so what is V of T to set 4? Let's see, we might have to convert this back to a list. Let's see. G dot edges V of T. Maybe let's see what happens. These are the edges that contain vertex 4. You see that? Okay. Now, how do we get the cost of an edge? Okay. How do we get the cost? Well, so maybe we can write a function to get, so the cost of edge 4, 2. So if we do G 4, 2, weight. That's the weight. And what's the weight of 4, 5? 4, 5 weight. That's the weight of that edge. And so it looks like we might need a way to simplify this. So each edge is a tuple. And if we put in the first node and the second node, we get the weight. So I'm going to write a function that just gives me the cost. So I don't have to type this over and over again. Okay. Now this script is getting kind of long, and I might break this up eventually, but for now we're just putting all of our helper functions in here. Cost. We want to know the cost in a graph G of the edge E. And the way that we're going to do this is we're going to return G at E0. So that's like the first node on that edge. And then E1, that's the second node on that edge. And then we're going to call weight. Okay, so this is a simple helper function. And then we can go to test, and we're going to import it, that helper function. Okay, so let's look at G dot. So let's look at maybe temp is equals to the list, or yeah, the list of G edges. And we're going to pass in the vertices of our graph. The temp edges. So these are the edges touching our tree. Okay. So we can look at the cost now. We can find the minimum cost edge by saying cost in G of temp edges 0. That has cost 4. That has cost 2. Now, one thing that we can do is we can sort temp edges. So if I have like a list like 3, 5, 1, 2, 7, 10, 6, and if I use the sort method dot sort, let me assign that to a variable. I'll call this like L. I'm just showing you how to sort things. So then L dot sort from least to highest, right? So if we could somehow sort this, but how could we sort that? Well, the way that we can do it is by calling what's called a lambda function. So we can do temp edges dot sort, and so the key is going to be, so we're going to say key equals, and then so lambda is a quick one-line function. That's all it does. So it's going to say it's going to take E, and it's going to replace each E with the cost of E. So what this is saying is that we're going to sort it, but we're not going to, these are tuples. We don't know how to compare these tuples. We're going to say that each tuple, each edge, and this is where the lambda function comes in. Lambda just says this goes to that. So basically, we're going to sort these by passing each one into the cost function, and in which we're going to sort it from least cost to highest cost. Oh, where is it? Oh, We have to do this with respect to the graph G. Okay. So I do that. And then if I look at temp edges now, it should be sorted in the correct order. 4, 5, 4, 2. So this has smaller cost. Okay. So, okay. We know that the min edge, so we should probably write a function to do this. So, yeah, we'll call this maybe, yeah, possible edges. Maybe something like that. And then for G, with respect to T, now we'll say that we're going to say temp edges equals list of G dot edges of the, and all the edges that have a vertex in T. Just like we did over here. Right there. Okay. But now we've run into a problem because I know we're running out of time, but suppose like suppose we're iterating through Prim's algorithm, right? So here we would add that edge there. And then that's a possible edge, that's a possible edge. Right there. And then possible edge, possible edge, possible edge. So you can do this one. And then possible edge, possible edge, possible edge. And then we get to there. But then we see that if we add this edge right here, we get a cycle because both endpoints are in the tree. So let me just go ahead and do this. So we added edges 2, 4. So 4, 5, 2, 4, 2, 3, and 1, 3. Okay, so let me just do that. So let's just say that we return this. All right, so just run that. All right, so here's T. So I'm going to do T dot add edge. So we added 4, 5. So T, so if we do E of T, V of T, okay. So E of T, V of T, okay, that looks good. So if we do T dot add edge, the next one we added was 2, 4. You can do this all at one time. I'm just trying to show you how to add edges one at a time. T dot add edge 2, 3. And then we added the edge 1, 3. Oops. Add edge. Okay, so V of T, V of T. Now, looking back at the picture, we know that we can't add 1, 2, right? Because that would make a cycle. So if I call this function possible edges, so look at all those edges, right? So the edge 1, 2, we surely don't want to add. But then also, this is our current tree, 2, 3, 3, 1, 4, 2, 4, 5, those edges. Those are all inside of here, right? So we need to get rid of the edges that we can't add. And what are the edges that we can't add? We cannot add the edges that have both endpoints in our vertex set, right? So for example, the edge 3, 1 is in there. Here's the edge 1, 3, that's the same thing. Both of those vertices are in our vertex set. So we know that this edge is already in our, it's either already in the tree, or like the edge 1, 2, it's not in the tree, but both vertices are. So if we add it, that makes a cycle. So we need to get rid of those. So what we can say is, okay, so we can say edges equal the list of E. So I'm using list comprehension now for E and temp edges. And again, this isn't the best, like the cleanest way to do it, but it's we can always fix it up later. So E for E and temp edges if so what do we want? We want only one of these vertices to be in our current vertex set. Or another way of saying this is, if this isn't in there, then we want it. Or if this isn't in there. So think about De Morgan's law. We want that not in there, or that not in there, right? So if E0 not in V of t. So you can split this up like this. So E for E and temp edges if E not in these VT, or the other endpoint not in. Okay. All right. So what goes in edges? The edges inside temp edges if the first endpoint is not in the vertex set, or if the second endpoint is not in the vertex set. And then we're going to return edges. So what we can do is just get rid of that. And we can just return this list here. Okay. And really, we don't even need to define temp edges. We can just say, let's just go ahead and copy that and put it right here. And then just get rid of that. There. So we're returning the list of all edges E for E in the edges in G that have vertices in T only when the first endpoint is not in T or the second endpoint is not in T. So now, if I look at possible edges, 4, 2, 4, 5. Okay, wait a minute, that doesn't look right. 4, 2, 4, 5, 4, 2, 4, 5, 4, 2, 4. So it looks like we need to fix that helper function. Okay, so let's see, what is going wrong here? So previously it did this, so So what did our tree look like? So if that was not in there, oh no, I need to add all those edges. That was it. See, like this is V of t, this is E of t. We need to add those edges, so add that one. Where's the other one? Add that one. Two, three. Four, five. So now E of t, E of t. Okay. So now if I look at possible edges, here we go. I'll just write it again. Temp edges equals possible edges B and T. 1020. So let's look. 1020. Those are the only possible edges. So now we just have to find the min cost edge. But it looks like we've run out of time, so let's go ahead and call it a day. I gave you plenty of things to do. So all that you really have to do now is to, so this works. Now you need to take this, put it in functions. And in here, you need to write another function called def min trims edge. So you have a graph G, T. You need to fill this in. And then once you do that, you'll have all the functions you need. And then inside of algorithms, you can come down here and say from functions, import min trims edge. I think that's what we called it. Yeah, min trims edge. After you write that algorithm, that function, you haven't done it yet. And then here, you would do def trims and then you'd have a graph G, and then a starting vertex. And this would return your minimum cost tree. Okay. And then once you have, so here you just need this and you literally write Prim's algorithm and you should be able to get it out. But yeah, we'll finish this up in the next lecture. And then after I post my next video lecture, you should have everything that you need to, together with a few people, write a nice little package to solve this thing, okay? So I will go ahead and call it a day. And then also for my Tuesday, Thursday class, I'm thinking about opening up the first exam one more time, but I have to consult with Mr. Nguyen first because I already opened it up once before. Okay, so I hope everyone says stay safe, and I will see you next time.